In this video, we are going to explain the trends found in the periodic table. So we're not going to, looking up the trends is easy. Explaining the trends is a little bit harder. So if you've seen this sheet before, this is one of our first lessons where we just wrote them down and figured out the trends, right? So we're going to be looking at electronegativity, ionization energy, and atomic radius, not necessarily in that order. So electronegativity and ionization energy are directly linked. In other words, electronegativity is the pull on the electrons. Ionization energy is the energy needed to pull it away. So if one goes up, if the electronegativity goes up, the ionization energy has to go up. It's like saying if you have a stronger grip on something, it's going to be harder to pull it away from you. That's literally what it's saying. So as we go down the group, the electronegativity decreases. Therefore, the ionization energy decreases, making Fr the lowest electronegativity and the lowest ionization energy on the whole table. As we go to the top right, or as we go to the right, the electronegativity is going to increase and the ionization energy is going to increase. That would technically make helium the highest in both, but it's not, and there's a reason. It is the highest for ionization energy, but because it's a noble gas, like this whole group, they don't have electronegativity. So the electronegativity award goes to fluorine. It's the strongest on the whole periodic table. It would be helium, but helium doesn't need electrons, so it basically doesn't participate. Therefore, it can't do anything. The double dash doesn't mean zero. It means it doesn't have it at all. So fluorine's the most electronegative, but helium has the highest ionization energy in the periodic table, because while helium doesn't need electrons, so it has no electronegativity, good luck trying to pull an electron away from a helium. It does not want to lose it at all. All right, and then atomic radius, that's a little different. As we go down the group, the atoms get bigger. As we go to the right, they get smaller, making helium the smallest element on the periodic table, making Fr the largest element on the periodic table. Now, the reason why is a different story. It's a little more complicated. So there's a couple things. There's the electronegativity changes as the atoms change in size. That causes the attraction between the electrons to change, which will then cause the ionization energy to change. They're all interlinked. So let's first talk about size. So the atoms get bigger as we go down the periodic table, and there's a very good reason for that. As we go down the periodic table, you're adding orbitals, and so adding orbitals adds a whole nother layer to the atom, and the atom is going to gain size no matter what as you go down. That's going to be very important. And if you notice, I highlighted the nucleus and the valence electron on these, and I'll come back to that in a second. As we go to the right, the atoms actually get smaller. And the reason they get smaller, and this one throws everybody off, because if you look at their masses, the atoms are getting heavier, they're having more protons, they're gaining more electrons. So if you're gaining all these things, well, why are you getting smaller? Because normally with people, if you gain all these things, you're going to become a larger person, right? That's like bigger people are heavier than smaller people, and that's because they have more mass. But in atoms, because they're 99.9% empty, they can still gain things and actually have room to shrink. All right, so they're actually becoming more dense as you go to the right, and there's a reason. We know that opposites attract, and so if we go to the right, I'm only drawing one orbital, but let's say this for lithium, there should be two. I'm just, for simplification purposes, I'm only going to draw one. And so as you go to the right, the nucleus gains protons, so it becomes more positive. The orbital that you're in doesn't change. You still have the same orbital. Your valence orbital is not, you're not gaining valence orbitals. What you are gaining is protons and electrons. So now you get more positives and negatives, and they're in the same orbital. So as the nucleus becomes more positive and the orbital, that's the valence, becomes more negative, the attraction between the two increase, making them contract and get a little smaller. So as we go to the right, we end up getting more protons, which means the nucleus becomes more charged or more positive. The pull on the electrons becomes greater because pluses and minuses are increasing. Therefore, the atom actually contracts. We call that pull. That literally is the definition of electronegativity. Now, as you go down a group, even though the same thing is happening, you are gaining a lot more protons as you go down, and you're gaining a lot more electrons every time you go down. You're also gaining an orbital. And it turns out that the distance between the pluses and minuses are actually more important than the amount of the strength of the magnet is less important than the distance between the magnet. And then we see that true in everyday life. Some magnets we know are really strong and some aren't. But if you've ever played with them, if you've ever played with two magnets or one magnet in a fridge, your fridge is basically a magnet, right? You know that when two magnets are really far apart, they don't attract at all. That's why magnets don't like attract from across the room to the fridge. And as they get closer and closer together, eventually you start to feel a little bit of pull between them. And then eventually, if you get them a little bit closer, so a lot of times the magnets will just kind of like snap out of your hands and snap together, right? That's because the distance is more important than the actual strength of the magnet. Now, stronger magnets will do it from a little bit further away than a weaker magnet, but a tiny bit further away for a huge increase in magnetic strength. And so distance is much more important than the actual strength of the magnet in terms of their attraction for opposite charges. So the increase in size actually negates the fact that the orbitals are, or that the nucleus is getting stronger and the orbitals are getting more electrons. All right, so let's do one full, so that's the basic size comparison. From this point on, I'm just going to do one full trend at a time. So let's start with the right. So we know as you go to the right, the protons become more positive, that's the nuclear charge, or the nucleus becomes more positive because it gets more protons. The pull on electrons increases, the atom gets smaller, and the electronegativity increases. Well, if the pull on that electron is getting stronger, then the reason the atoms get smaller is because we have a stronger attraction. So I kind of like explained 1 and 2 together. That's so as the electronegativity increases, the atomic radius is going to decrease because you're going to pull your orbitals in tighter, making your atoms get a little bit smaller. Therefore, if you want to remove those electrons, right, from like this atom, it's going to be way harder to remove it from this atom than this atom. And the reason is more attraction, more pull, so therefore it's going to be harder to get it away. So that is the attraction is the electronegativity. The atomic radius gets smaller, the atom gets smaller because of that, and it becomes harder to remove an electron because of that attraction getting greater. All right. As we go down, the protons do become, you get more protons and you get more electrons, but the adding of orbitals totally negates that and actually makes the valence electron be much further away. And so the atomic radius gets bigger. The distance between the positives and negatives increases because of those orbitals. Therefore, the attraction between them decreases. I kind of lump 1 and 2 together. And then if you want to remove that most loosely held electron, which is the valence electron, it's going to be much easier to remove it because it's much further away from the source that's attracting to it. So you're not going to have as hard a time pulling it away. Now, the term I use is called nuclear charge. Nuclear charge is just the magnetic strength of the nucleus. And I do want to show you one little trick. If you were ever stuck on these trends, rather than looking up everything I did here, there's a real easy way to do it. Just focus on 3 elements. If you look up lithium, francium, and fluorine, right, you'll know all of it. Meaning, if I just look at lithium, let's say the trend is let's say the question is, what's the trend in electronegativity? Well, lithium's 1, francium's 0.7. It's going down as you go down. Well, let's look at as we go to the right. Lithium's 1, fluorine's 4. Well, it's going up. And so all you have to do is use those 3 elements and you can find the trend, okay? The trend may weave a little, like if you notice like ionization energy, it jumps a little, like it goes down from 403 to 376, but then back up to 393. We don't care about that. We're looking for the general trend. In general, it's decreasing as you go down and it's increasing as you go to the right. And rather than looking up all the elements, just use these 4 or these 3. And the reason I want you to use those 3 is if you accidentally looked up, let's say, RB and CS as the example, or CS and FR as the example, you might be mistaken if you pick 2 elements that are right next to each other. You might hit one of those instances where the trend isn't always followed. So if you pick something on the far left and the far right, that'll totally get rid of that, and that will never be a factor anymore. So that's a quick way of looking up the trends now that you've actually looked them all up and written them down.